Let's have this example. So for example, we have this beam carrying a 50 kN load. It is supported by a bronze rod and a steel rod. So these are the properties of each rod. Then it is hinge support at point A. We are required to compute for the axial stress for the steel and the axial stress for the bronze. So to determine the axial stress for the steel, we need the force for the bronze, the force carried by the steel, and the force to be carried by the bronze. So how do we determine those forces? Okay, let us use the three equations of equilibrium. Okay, our first equation, that is by summation of forces vertical equal to 0, upward forces to be positive. So I'll be assuming that AB, or the vertical reaction at the hinge support A, will be upward. So the same with the force to be carried by steel, upward. By the force to be carried by the bronze, also upward. So we have the upward force, that is A vertical plus, we have PS plus PB minus 50 kilonewtons is equal to 0. We have the vertical reaction at A plus the load to be carried by the steel plus the load to be carried by the bronze is equal to 50 kilonewtons. So let this be our first equation. Then the second equation of equilibrium, that is the summation of forces horizontal equal to 0. But for this case, it is not applicable for a reason we don't have a horizontal force. Okay? So we don't have a horizontal force. The next is by summation of moment at A. I'll be doing summation moment at A equal to 0. Clockwise moments to be positive. So that is the same as PS, or clockwise moment, with respect to A. That is 50 multiplied by 1.6 plus 0.8 is 2.4 minus PS, how far from A, that is 0.6, plus PB, how far from A, that is 1.6 equal to 0. So we have, this is also minus, since also counterclockwise. So with respect to A, PS and PB are both counterclockwise. So we have 0.6 of PS plus 1.6 of P sub B is equal to 100.4 plus 50 is 20. This is equal to 120 kilonewton meters. Let this be our second equation. As you can see, we have used the three equations of equilibrium. Okay? And we cannot use any other equation. So it means the three equations of equilibrium are not enough to compute for the unknown. So it's for this unknowns. So it means we can conclude that this setup is basically statically indeterminate. This is statically indeterminate, which means summation forces vertical, summation forces horizontal, and the summation of moment cannot be used to compute for the values of these unknowns. So we can apply axial strain. All we have to do is imagine the exaggerated form or position of the beam. If there will be a deformation for the steel and deformation for the bronze. So for example, because of this 50 kilonewtons, the beam will go down if there will be deformation for these two supports. So initially, let us imagine that this is the beam. So the right end will go down because of this 50 kilonewtons. If there is a deformation for the bronze, let's say delta B, and a deformation so this is the deformation for the bronze and the deformation for the steel. So this is just an exaggerated representation of the deformation of these two supporting rods. So this distance is basically 1.6 meters. This is 0.6. Then we can have an equation by ratio and proportion of similar triangles. So by ratio proportion of similar triangles, that is the same as delta S. The deformation of the steel is to 0.6 is equal to the deformation of the bronze is to 1.6. So from that equation, we can have a relation between the axial force of the steel and the axial force for the bronze. So we can have the deformation of the steel is equal to, that is 0.6 divided by 1.6 of the deformation of the bronze. By the way, what is the equivalent of deformation last time? Deformation is the axial force, the length, divided by the area times the modulus of elasticity. So let us use this equation. Alright, we have the equation. This is delta S is equal to 0.6 divided by 1.6 of the deformation of the bronze. Alright, from this figure. So what is deformation of the steel? That is the load to be carried by the steel. What is the length of the steel? That is 1 meter divided by cross-sectional area of the steel. We have 600 square millimeters. Then the modulus of elasticity of the steel is 200 gigapascals. And then this is equal to 0.6 divided by 1.6 of deformation for the bronze. That is Pn over Ae, the load to be carried by the bronze. The length of the bronze is 2 meters. Divided by area of the bronze is 300 square millimeters. Then the modulus of elasticity of the bronze is equal to 83 gigapascals. So let's have, what will be the equivalent of the load to be carried up by the steel in terms of the load to be carried by the bronze. So computing for that value, as you can see, no need to do the unit analysis since all units on the right side of the equation is basically equal to the units on the left side. So all units will be cancelled out. So meter, square mm, gigapascals, gigapascals. So we have 0.6 of 2 divided by 1.6 multiplied by 300 by 83. That is multiplied by 200 by 600 divided by 1. This is equal to 3.614 of P sub B. So you have PS equal to 3.614 of P sub B. We go back to our equilibrium equation by summation of moments. We have that 0.6 of PS plus 1.6 of P sub B is equal to 120. So this is equal to 0.6 of what is the equivalent of PS. We substitute, that is equal to 3.614 of P sub B plus 1.6 of P sub B is equal to 120. So we have 0.6 of 3.614 plus 1.6. We have the value as 3.7684 of P sub B is equal to 120. By computing for the axial force to be carried by the bronze, that is 120 divided by 3.7684. We have this value. This is equal to 31.844 kilonewtons. So that will be the load to be carried by the bronze. Then the load to be carried by the steel. We are using this equivalent. We have the PS is equal to 3.614 of P sub B. Is equal to 3.614 is the computed value of P sub B. Is equal to 31.840 4 kilonewtons. Okay, the load to be carried by the steel is equal to, we have 31.844 times 3.614. So we have 100. This is 115.084 kilonewtons. So this will be our the load to be carried by the steel. So we have the stress to be carried by the steel is PS divided by area. Okay, we have the load is equal to 115.084. Okay, we are multiplying times 10 raised to 3 to begin. And newtons are basically multiplying by 1000. Divided by area of the steel is equal to 600 square millimeters. So we have the stress of the steel, or the stress in the steel rod is equal to, we have 115.084, this is times 1000 to be in newtons, divided by 600. And we have the stress is equal to 191.807. Newtons per square millimeters is the same as the megapascals. So this will be our answer for the stress in the steel rod. And lastly, we have the stress for the bronze is the load for the bronze divided by area. We have stress carried by the bronze material. The load is equal to 31.844. It is times 10 raised to 3 to be in newtons. The area of the bronze rod is equal to 300 square millimeters. So we have the stress carried by the bronze rod, 31.844 in newtons, so multiplied by 1000 over 300. And we have the stress for the bronze equal to 106.147 newtons per square millimeter is equal to megapascals. Okay, so this will be our answers.